Hello, good afternoon. Thanks for coming. I'm Ian. I'll present for the first half of our talk, and then I'll hand over the stage to Alex. We're here to tell you about adversarial examples. Adversarial examples are inputs to machine learning systems that are intentionally designed to cause them to malfunction. It looks like there's an object in front of them.
Okay, well, that's loud. All right. So, to begin the talk, I'll describe a few really basic machine learning terms to make sure that everything makes sense for the rest of the presentation. The goal of machine learning is to train what we call a model. The model is able to process new inputs and figure out how to do things that would be difficult for a traditional computer program. The way that it works is we have the model learn to process training data correctly. So training data can be things like collections of images with labels, where we say this photo is a photo of a car, this photo is a photo of a bicycle, and so on. For example, in our work, we trained our machine learning models on the ImageNet dataset. The result of the training process is a set of values of parameters. Parameters describe how the model should behave, and by finding the right value of them, we can make sure that the model maps each input to its correct output. At test time, the input that we receive is just a photo. We don't actually get a label telling us what's in the photo. It's the job of the model to guess that. So an adversarial example is an input that we show at test time. There are a lot of different ways that you can imagine there being problems for computer security involving machine learning. For example, you could imagine supplying training examples at training time that make the model learn the wrong thing. Or you could imagine examining the model at test time and recovering training examples that were intended to remain private. What we're studying in this project is the things that can go wrong if an attacker provides a malicious example at test time, a malicious input. The basic idea of the attack that we're presenting is that we would like to make an image, or the attacker would like to make an image, that the machine learning model classifies incorrectly, while the image simultaneously looks very, very normal to a human observer. In some cases, if we're very successful, the image might not even look like it's been altered in any way. And then in other cases, more commonly, it might be easy for the human to recognize the content of the image correctly. So this is an example input here, where before it's been modified in any way, both a machine learning algorithm and a human correctly recognize this image as being a school bus. We can make a very small modification to this image, where it is now recognized by the machine learning algorithm as being an ostrich. But to a human observer, it still looks exactly the same as a school bus. In general, we can use gradient descent to generate many different kinds of adversarial inputs. Each of these panels of images here are animations. You read them left to right, top to bottom, like reading a book. And every panel looks more or less the same. That's because the changes are very small, and they don't really show up as causing a difference to a human observer. But to a computer program, they actually cause a very large difference. In each of these animations, the object at the upper left is correctly identified by the machine learning algorithm. So, for example, this is identified as a ship, this is identified as a car, this is identified as a cat, and so on. Each of the animations shows the image gradually change until in the lower right, it is actually recognized as being an airplane. So this ship, this cat, this car are all recognized as being airplanes by the machine learning model. We make these images by following the gradient of the probability that the model assigns to the airplane class and modifying the input pixels to increase that probability. In most cases, you probably can't see that anything changed. The only place where I see anything changing myself is the photo of the cat, where the color of the cat's face changes. But in most cases, there isn't really anything that makes the image look more like an airplane at the end than at the start. We can also make these images very, very quickly using a single step of the gradient. We use a special trick where instead of calculating the gradient itself, we just calculate whether each pixel should increase or decrease in value. And if we add a very small increase or very small decrease to each pixel, we will get a misclassified image in a single step with very high probability. In this example, we start off with a panda that's correctly recognized as a panda. And then we have this image here that tells us whether each pixel should increase or decrease if we want to confuse the model. We add just a little tiny amount of an increase or decrease to every pixel, and the result is this image of the panda over here. If the two panda photos look the same to you, it's because they actually are. The monitor is only displaying the image at 8 bits of resolution in the color channel, but it's presented to the machine learning model with 32 bits of resolution. We've made such a small change that the 8-bit representation stays the same. And despite the change being so small, this actually fools the machine learning model, and it's now recognized as being a given rather than a panda. Another interesting thing is that the machine learning model can tell you whether it's confident or not confident. At the start, it's not particularly confident that this is a panda. It thinks that there's a 60% chance that it's a panda. At the end, it's very confident. It thinks that there's a 99.3% chance that this is a given. And that means that the adversarial crafting process is able to make images that the model is much more confident about than images that appear in reality. We can make a map of where adversarial examples lie in input space. So what we're doing is we're thinking of the space of all possible images. Let's say the space of all 1 megapixel images as being a space with 1,000 dimensions. And we can't plot 1,000 dimensions on the projector. So what we do is we make a 2-dimensional cross-section of that space. We make a horizontal axis that measures how far we move in the direction of the adversarial example. We make another axis, a vertical axis, where we move in a random direction. Then each of these plots over here is showing what happens in the vicinity of a different image. So this little cell is for one image, this little cell is for another image. Everywhere that we see white in one of these maps, that's a point that the classifier classifies correctly. So in the very center of each plot, just a little bit of where, a little bit to the left of where the white patch ends, that's where the naturally occurring image is. And that's almost always classified correctly because the model is very accurate. As we move to the right, we go into an area that has a different color. Each of the different colors represents a different category of object, other than the correct category. In each image, we colored the correct category white, so that it's possible to see when the model is correct or incorrect. So as we move in the direction of the adversarial perturbation, we find that about half of the input space is misclassified. If we move in a random direction, not very much changes. If we begin in the middle and we move straight up, we remain correctly classified. So random noise isn't enough to confuse a machine learning model. But if we know more or less which direction to move in to generate an adversarial example, about half of the space will actually confuse the model. And it's difficult to figure out exactly which half that is because there's so many different directions you can move in. But if you have a reasonable estimate of that direction, you can confuse it very easily. Also, if you just feed completely random inputs to a machine learning model, most of them will be processed in an irrational way. So here we just sampled random noise, and everywhere that a noise image has a pink box around it, the model thought that this noise was something rather than nothing. In most cases, it thought that the noise was a horse. And then we also tried to see if we could make it think that the noise was specifically an airplane to actually try to control the class of the output. Everywhere that you see a yellow box, we did one step in the direction of the sign of the gradient, and that turned the image into being an airplane, according to the model. That happened about 25% of the time. So if we were a malicious attacker trying to get the image to be recognized as an airplane, we would need about 4 attempts before we'd succeed. And airplane was the hardest class. Keep in mind that if we started with the horse class, we wouldn't even need to do anything. We would just start with a random input, and it would probably be classified as a horse. One thing that's very interesting about adversarial examples from a security point of view is that different machine learning models are usually affected by the same adversarial examples. Here I'm showing you the weights of 2 different logistic regression classifiers. Both of these logistic regression classifiers have been trained to tell 3s apart from 7s. And they're trained on 2 different training sets. Here's the training data for this one, and here's the training data for this one. Because they're both learning to solve the same task, they learn more or less the same weights. That's why they generalize from the train set to the test set. But that means that adversarial examples also generalize from one model to another. It turns out to happen regardless of whether the model is trained on the same training data, or even whether the machine learning algorithms are the same for both models. You can actually create adversarial examples that were designed to fool a deep neural network, and then use them to fool a decision tree. This grid shows the success probability of that kind of attack. As long as the two models were trained to solve the same task, they're very likely to actually be vulnerable to the same attacks. That means that you can attack a remotely hosted model even if you don't know which algorithm was used to create that model, and even if you don't have access to that model's training data. You just train your own model to do the same thing, and there's a very good chance that your attack will transfer over. The basic way that you can do this is you start with looking at a target model that you'd like to attack, and you figure out more or less what task it's solving. If you can, you get access to its parameters or description of the model. But if you can't, you just start by training your own model. You can either do it by collecting your own training set, or if you don't have the resources to collect your own training set, you can send different inputs to the target model and see what outputs it produces. And you can use that to reverse engineer the model. After you reverse engineer your own copy of it that we call the substitute, you can design your own adversarial inputs for your substitute copy, and then send them back to the target. And the target will probably misclassify them. We were able to test this against a variety of remotely hosted APIs, where we actually don't know what the API is using internally. And we were able to fool all these different APIs over 84% of the time. This was using both MetaMind, Amazon, and Google Cloud Platform machine learning APIs, where we can upload data sets and these services will train a model for us, but we don't actually know how that model works internally. We're still able to reverse engineer it and break it. I'll let Alex take over for the second half of the presentation.
So, as Ian mentioned, well, there's such phenomenon of adversarial examples, and it could be quite annoying to see that your machine learning algorithm breaks by just very small changes in the image. But then, what he talked so far, one important aspect that all input images are directly fed into the classifier. In particular, as he said, for one of the examples he provided, he would exploit the fact that he can use the Claude point precision. So now let's imagine a slightly different scenario. You don't directly feed your data into a machine learning system. You instead take a picture of it, you record it through the microphone or do something else. So basically you use some physical world sensor to perceive your data. Well, in this work we concentrate only on images, but we believe it could be extended on other types of data. So now let's say you have a camera and you try to perceive your image through the camera. And now the adversarial, it's become much harder to construct a adversarial example, because in the previous case, you have fine-grained control of every pixel and you can adjust it slightly, and basically you can construct whatever you want. If you use camera or any other sensor, then typically you don't have fine-grained control of the image which fed to the neural network. And then the question arises, in this case, when you don't have fine-grained control and you perceive data through the camera, can you still do the adversarial attack? So to prove this, to show if it's possible or not, we did the following experiment. We printed a bunch of images, printed pairs of clean and adversarial image. Clean is the unmodified image, adversarial is the one which is with this perturbation. We took photos of them and then tried to recognize them. And we noticed that, well, not always, but pretty often we still can fool the system. So answer is yes. Even if we perceive data through sensors, like a camera, which cause its own perturbations, we still can fool machine learning systems. Just to reiterate and make it a little bit clear, so this is the previous case when we directly feed image into the machine learning system. So in case of clean image, we have a file essentially which we upload or somehow feed to a classifier and get a class. Then we apply adversarial perturbation, get another file where we control every pixel, we can feed it to a system and get another class. Now what changes in this experiment, so then we add a step of printing and making a picture. And even in this case, we're still able to fool the image classifier. So this is how our experiment looked like. So this is essentially images we generated. This is like a pair of clean image, which without perturbation, and adversarial image. Then we printed them and take a photo. This like photo look like. For this photo, we cropped basically the images and got these pictures of the crop animal. If you ask about the QR codes, the purpose of QR codes, the only purpose of QR codes was to simplify cropping. Because we not study how to crop image in this research, we study how to fool machine learning system. And another thing, the QR code encoded the set of which batch of adversarial images we use. So yeah, eventually we printed, we took a photo, we cropped the image and ran through the classifier, and we noticed that up to 87% of images could still remain adversarial, such non-trivial image transformation. Well, if it's not completely clear, now I'll show you the demo, which I hope will make it clear. For the demo, I have an app on my smartphone. This app just runs some TensorFlow model with the image classification. And for the demo, I created a bunch of images like, let's say like this one. This is the source image. And yeah, this is, the end can show the adversarial image. In this case, it's a pretty extreme case. If you look carefully, you can see that there is a lot of noise. But still, from the human point of view, this is still the same image. And less extreme case, let's say, this compares. If you come close and look carefully, you can see some small noise. If you probably, especially from back rows, but probably even from front rows, you cannot see much difference. So yeah, now I'm going to show you the demo.
So Alex will set up the screen to show you what his phone can see, and he has a copy of an Inception network running in TensorFlow on his phone. So it will provide live classifications of everything that comes in front of the camera. And then, I know that in the back you can't see these photos very well, but you'll be able to see them clearly on the projector when you can see them through the lens of the phone. So we're starting with the photo of the library that we showed you a second ago. If you look at the projector, you can see that that's recognized as being a library. If you read the text at the upper left side of the screen, it's recognized as being a library with about 90% probability. Now Alex is moving the phone to look at the adversarial image of the library. You can see that it's now classified as being a prison, and that it has about 30 to 60% probability of being a prison, depending exactly how he holds the camera. As another example, we have an image of a washing machine. Alex is aiming the camera at the clean image right now, and it's correctly recognized as being a washer. This one is a little bit more of a difficult image, so it has relatively low probability of being correct. And now we're looking at the adversarial image. It's being classified as a doormat. So these are photos that have been printed out, but you could imagine putting paint on physical objects or on a person's face to confuse robots, facial recognition systems, document reading systems. In general, this shows that it's possible for an attacker to fool systems in the physical world. We have another image of two different washing machines. This one is recognized as being a washer with about 30% probability. Is this one the clean or the adversarial?
I think it's clean.
Okay.
Sometimes, so this one is not very confident, but it depends on the light.
Yeah.
Well, yeah, it depends on how I hold the camera. Basically, it's usually classified as washer.
This one is also classified as washer.
Maybe this one actually clean. Yeah, that's probably this one the clean. This is the adversarial, but it's a small.
So this one occasionally gets that it's a washer, and also think it's a safe and a switch and a loudspeaker. The two images look similar enough that we actually lost track of which one is which. Now we're looking at one that has more obvious noise, and this one is consistently recognized as being a switch or a combination lock. All right, so that's the extent of the.
We have one more slide.
Okay. Yeah.
So now I hope we scared you a little bit, so you won't trust the data machine learning systems. But we still want to say that it's not as bad as it looked like. First of all, the demo which we show, well, it's a demo, it's a proof of concept, but it's not that easy to do in practice, to do this attack. First of all, the 80% adversarial images, basically the 87% number which I told before, this is only for one method, and it seems like you could, well, the fast gradient sign method which I mentioned before. And for this method, constructing serial examples seems like you can resist them. For other methods, the number will be much lower. Also, in this particular case, when we get this 87% number, we knew exactly machine learning weights of the machine learning classifier, which typically not the case for the real world attack. Well, in the real world, you don't really expect that you know the internals of machine learning, and so as Ian mentioned before, you still can do the attack, and in particular, when we did this before, I believe this is the black box attack. We didn't know the weights when we generated adversarial images for the phone. But it's much harder. And the most important thing that what I showed you, you see the class changes from like washer to doormat and so on, from library to prison. But in these cases, we found these examples, but we didn't really control the destination class, the target class which we want to change to. And when you do a real-world attack, let's say you try to fool face recognition system, or you try to fool a system which recognizes better checks, you probably want to make sure that the check of face will be recognizable, like very specific, like number, very specific person. And this, for this kind of attack, we noticed that it's actually pretty hard to achieve, especially when you do such real-world attack. So, well, that's essentially all that we have. Well, thank you for your attention, and we're ready to answer your questions.
Anybody? I'm just wondering your opinions regarding why this is a false classification. Is it because you basically add a noise and you change the way that the neural network how they do the classification, or it's just because the neural network is not big enough?
So we tried to keep some of the machine learning details a little bit light here. But if you look at our research paper, we wrote a paper called Explaining and Harnessing Adversarial Examples, where we explained that most machine learning models that exist today make very linear predictions. And a linear function tends to extrapolate very poorly. Say that you've usually shown inputs around the size -1 or +1 to your machine learning model, and then suddenly you show an input of size +2. A human being might say, it's very unusual to see a +2, so I should be less confident about what I'm going to say. But a linear model will actually double its output and become much more confident about what it's seeing. And we think that even though neural networks are described as being very nonlinear, when we measure the way they behave on unusual inputs, they tend to behave very linearly.
So that the added pictures mostly look like the noises. So I'm wondering if the algorithm like has lots of regularization or other noise reduction procedure before doing machine learning, or in their training data set they already added those noise to train. Will your method still be such effective?
So the best defense is to train on adversarial examples. And
anything else you were saying?
Well, basically, we're still working on the defenses and the part of ongoing research, so we won't talk too much, but yeah, this is one of the ways to defend, and we're going to publish papers soon, but it's still, it helps, but maybe not always. So yeah, to some extent it might help. Also regarding what you said about like do some pre-filtering, the important question is any filtering you could consider like as a prefix to machine learning system, and you still can do gradient descent through machine learning system and this prefix and construct adversarial examples given, assuming that you do pre-filtering. And in this case, well, you still get adversarial examples. So pre-filtering won't help you, won't fix the problem. It might still also reduce the chances, but it won't fix the problem. And yeah, regarding adversarial training, we are going to publish papers soon, so basically you can read more details there.
In general, with security, you need to think about whether the attacker is going to adapt to your defense. So there are a lot of defenses you can add that will remove one specific vulnerability, but then an attacker who is aware of that defense will just make a different attack, and they might still be able to succeed at the same rate that they were able to before.
Sorry, I have another question. So, this one you talk about image recognition. So basically, you consider every pixel as a feature, right? So many like written recognition, they will do some feature extraction first. Like instead of just take every pixel as a feature, but they will extract a lot of other features even in different frequency space. So I'm wondering if you don't know their feature set, or is still the algorithm will be very effective.
Yeah, so far we haven't really had any trouble breaking anything we've tested. In general, if the defender is using an algorithm and we don't know what kind of algorithm they're using, we train a neural network to imitate their model. Then we make adversarial examples for the neural network, and those adversarial examples will also be misclassified by the target with very high probability.
So have you tried this on any other machine learning problem other than image recognition? How about like voice recognition?
There will be another speaker today talking about
Yeah.
voice recognition. Yeah.
Any other questions? Okay, I have another question. Instead, it is very hard to fool the classifier to specific target. But in fact, it is still very dangerous for auto driving. If we just fool the car for the car not to recognize the stop sign, then they will be very dangerous. Right?
I would clarify that it is hard to do this when you do the black box attack and using camera. Yeah. If you have a full access to the model and you can do whatever you want, then it's actually not that hard. So regarding the second part of the question about the car and stop sign, I think in this case it's much easier to just like go at night and like cut the stop sign completely. So it's kind of overkill. Another thing that especially with the modern cars, they have a lot of, they're basically connected to internet, and I bet they have a lot of other much security vulnerabilities which is much easier to exploit.
So it's also possible to exploit a human driver. People are very easy to confuse, but I do think that there are vulnerabilities in self-driving cars, or the potential vulnerabilities if people are not careful with the machine learning systems they design. I don't think that the things that can happen with self-driving cars are much worse than what could happen with human drivers, but it might be harder to tell that something malicious happened. That if somebody used adversarial examples to make a self-driving car misbehave, it might look like it was just a glitch, rather than somebody intentionally causing a problem. But if you go to fool a human, if you put something really confusing in the road, or if you remove the stop sign, then people will know that it was malice. And in this case, people might not realize it was malice and might think it was just a defect in the car's software.
Shall I please give a pass to
So I think this is really cool talk. Today, machine learning is so powerful to solve a lot of problems and provide valuable tasks for new applications such as autopilot and so I think, but the thing is, most machine learning systems today are vulnerable to adversary case, like you mentioned. So you guys should very cool demo today, just with a real picture from camera to show confuse the classifier to get completely wrong results or just not accurate. So that's really cool. So I think because AI will become more and more important and influence our life in the future. So we really
The second talk is by Adversarial. Adversarial Waidia is a PhD candidate in computer science at Johns Hopkins University. His research broadly focuses on network security and privacy issues in emerging technologies as well as cyber physical systems. He will present the line of rising attacks against voice interfaces powered by machine learning. Welcome, Adversarial.
Thank you.